Go. Hi, everybody. We're ready to start into the second half of chapter 2. We're looking at 2.4, 2.5, 2.6. We are going to continue examining limits. In 2.4, we're going to learn about these things called limit laws, and we are going to look at three major techniques for determining the limits of functions, here at least that are early on. So that's what's coming up. In 2.5, we're going to talk about the idea of continuity with, maybe a little bit more precision than we have so far. I've tried to forecast and introduce the idea of continuity already into our language a little bit, but we should talk, a little bit more in detail about the idea of continuity. Um, and this won't come up until next time, but we will recap on the idea of velocity, and we're going to talk about the limit definition of the derivative. So we're going to get into a new branch of calculus with, derivatives. It's going to be good. Okay. So here at the beginning of 2.4, I'm trying to do kind of an advanced organizer kind of thing. So this is what we're expecting to see today, but I'm going to go through this too fast for you to be able to pick up on all of it, probably. Okay, so first major technique of finding a limit is just direct substitution. Sometimes we'll be trying to take the limit of a function that's already continuous, and it'll be really easy to just plug in the value that we are approaching into the function and get a y value out. So this limit does equal 7, but it's as simple as just plugging in the x value. Um, the next major technique involves some kind of algebra trick, and then we're able to substitute the c value in to evaluate the limit. And the first class of algebra trick is just factoring. So we can factor out, um, of a scenario where if we've got this quadratic over this linear term, um, both of those go to 0 if we try to plug in 6 right away. 6 squared is 36, so top goes to 0, bottom goes to 0. And that's an indeterminate form, and we wouldn't be able to evaluate the limit there. But if we factor the top, then we can cancel out the common x minus 6 factor. And when we're just left with x plus 6, we can plug in 6 into this x and get 12 as an answer. So sometimes factoring out this place where, we would have a hole in the function, because 6 wouldn't be part of the domain here. When we factor that out, we get an actual answer. So that's pretty cool too. Um, the next one is using the algebra trick of a conjugate. So if we have something that has square root functions in it, um, especially with a minus sign or a plus sign in between the two square roots, then we can change the sign in between them and multiply so that we have a difference of squares factor pattern, and things cancel out nicely, so that in the end, we're able to just plug in this value of 0. If we did it initially, then we would have another case of 0 over 0. But when we do it down here, it works out okay. We get an actual number for an answer. So conjugate will be the next strategy. And then the third major technique will involve the squeeze theorem or the sandwich theorem. Um, we mentioned this too earlier, as a strategy for when we have a function that is misbehaving. E to the x times sine of the x would continue to grow over time, but it would also continue to oscillate. And so we get this weird green oscillating pattern that continues to grow in amplitude. But if we can sandwich that in between two more well-behaved functions, and, you know, Then we can evaluate the limits of those more well-behaved functions. We're going to x equals negative infinity here. So this one approaches that horizontal asymptote. This one also approaches that horizontal asymptote at y equals 0. And so since this function that's always bigger, and since this function that's always smaller goes to the same limit, then the function that's always in the middle also has to go to that limit. So there's a whole sequence of ideas there, but squeeze theorem is the third major idea. So direct substitution and algebra trick, and then substitute, and then squeeze theorem. That's what's on the docket for today. Before we come back to those, though, I'm going to introduce some what are called limit laws. Um, these limit laws are things that are going to allow us to break up more complicated limits into smaller pieces and find scenarios where direct substitution is appropriate. So they're going to just be another tool in our toolbox. Right now, for today, I am going to just present these as laws. And for right now, it just seems like they're being handed down from on high. But in reality, if we wanted to show that these laws actually work in general, we would need to do epsilon delta proofs to show that these things actually hold true. So we would need to work with inequalities and epsilons and deltas, and that's just something that's outside of the scope for this course. If you really feel like you have an interest in that, though, you can take real analysis. Um, Jack and Gavin are in there right now, so if you want to ask them about real analysis, we're going to get to this kind of stuff there. We're going to work with those epsilons and deltas. But right now, this is cool. Let's take a look at the laws. Um, these can be summarized by, you know, with little phrases. Right now, we've got the limit of a sum of two functions equaling the sum of two different limits. So sometimes this is abbreviated. Um, the limit of a sum is the sum of the limits. And that's just a mnemonic device to remind us of what's going on. But what this says is that if we have a more complicated limit with a plus sign in there, it's okay to split that more complicated function into two different functions and evaluate the limit separately because those things will end up being the same exact thing. Same thing with a minus sign. We've got the difference law. Same thing with some constant multiple times the function. So we can always factor a constant multiple out. Here's the product law where we've got a product between two different functions. And the same thing with the quotient. So these limits um, play very nicely with functions being pushed together in different ways with different operations. So we can dissect things and make them simpler. Let's go ahead and try to use some of these limit laws on example 2. I'm going to go ahead and scroll down so that we have more space, but yeah, we can work here. Here we have a piecewise defined function. F of x is the absolute value of x over x if x is not equal 0, and it's 0 if x does equal 0. So it's defined this way because putting 0 over 0 is an indeterminate form. So technically, this wouldn't be defined at x equals 0. But if we plug in the hole by saying the value is 0 at x equals 0, then we're going to be good. Let's go ahead and think about what that function would look like. Let me scroll here. All right, so blah, blah. We're looking at f of x now. Um, the absolute value of x over x. Um, one way to simplify this is to look at the absolute value of x as two different functions, kind of its own piecewise function. Um, the absolute value of x is equal to x when x is greater than or equal to 0. Sure. So whenever you put a positive number in for x, you just get that same positive number out. Um, this one feels wrong, but I'll try to explain. When we throw a negative number in for x, the absolute value of x is the opposite of that negative number. So we're throwing in a negative number and we're getting a positive number out because we're doing the opposite of the negative number. So generally the absolute value of x looks like a v, like boom, boom. When we divide it by x, it's no longer going to look like a v. Um, it'll look like, okay, let's see. Let's go with purple. Maybe I'm going to change this color now. It'll look like x over x, or 1 for x greater than or equal to 0. And it'll look like negative x over x equals -1 for x less than 0. So the idea is this function would look like a negative horizontal straight line until we get here. And then it would pick up. Oh, actually, shoot, I should put another. Hold up. When we're doing this, I don't want that or equal to sign. I want that to be gone. Okay. It was fine to have the or equal to sign here because, 0 putting in for x is fine. But when we've got x over x, putting in 0 for x is not a good idea. That was the whole thing with this piecewise function. So x over x for a constant value of 1, negative x over x for a constant value of -1, and then 0 when x equals 0 means I would actually fill in the dot here at the origin. So that is this function, and it's a weird function. And that's kind of the point of this limit law, is that when we start looking at the product of these two functions, things start to look pretty complicated. But the beauty of the limit law is that we're going to be able to take this limit, and instead of looking at the limit of a product, we're going to be able to take the product of two limits. So we'll be able to say the limit as x goes to 0 of f of x as one thing, and then the limit as x goes to 0 of g of x as its own thing. So g of x is just cosine. Haven't said it yet, but that one's fine. Cosine by itself, the limit as, x goes to 0, let's go ahead and we can draw that real quick. Cosine looks like that. The limit there will be 1. So the limit for the cosine function will be 1. But for this other, purple function, f of x, this mess, notice how the left-hand limit does not match the right-hand limit, and neither of those match the function value. That doesn't matter too much, but mainly the left-hand limit doesn't match the right-hand limit. And yeah, this limit doesn't exist. So this one doesn't exist. You could look at the right-hand and left-hand limits separately and show that the right-hand limit for the entire function doesn't equal the left-hand limit for the entire function. But if one of these doesn't exist, then the entire limit is not, or yeah, the entire limit's not going to exist. Yeah, I suppose for completeness, real quick, I'll just write that. If we split it into left-hand and right-hand limits, the left-hand limit would look like um, limit of as x approaches 0 from the left, goodness, left, f of x. Um, that one ends up being -1. And if I did that times the left-hand limit for the cosine function, then that would be 1. And the overall left-hand limit would be -1. If I did the same thing then for the right-hand limit, the first limit going to 0 from the right of f of x, we'd go back into the purple function and see that that one's a 1. Well, and then cosine still goes to 1, even coming from the right. So this one would be 1, and we'd have 1 times 1 equals 1. So maybe it would be a little bit more proper to look at the left-hand limit and the right-hand limit separately for the entire function and say that those two things are different, so the overall limit doesn't exist. But yeah, when we get into this stage, that's an issue too. When one of the limits doesn't exist and the other one does, it means that the overall limit doesn't exist. Okay, moving on. Cool limit laws. Here they're showing that if you use the product law, you can come up with a positive integer power law if you just apply the product law with the function to itself. So that's another limit law that can be proven from the product law. Here are two statements that are used as building blocks. Basically, what this one says is that if you've got a constant function y equals 1, then any limit where x approaches any number c, the end result of that is always going to be 1 because you're just on a horizontal line. And similarly, if you are on a line with a slope of 1 that goes through the origin, the y value will always equal the x value. So, the limit as x approaches c will equal the y value of c will match up with the x value of c. Those two, along with the other laws, kind of form a basis for direct substitution. A polynomial is just a bunch of power, you know, different power parts of a function all into one. And, you can base it off of powers of this limit, this function where it's involving x. Um, Yeah, so utilizing the product law, the power law, the addition and subtraction law, um, you can make polynomials. And it is true for every polynomial that they are all continuous. And this limit, as x approaches c, equals the function value evaluated at c. Um, so this one says all polynomials are continuous. The next one even extends that into all rational functions, um, which is totally cool. This one I made a specific point to say they are continuous on their domains. So we are purposefully leaving out any parts where the denominator of this function would equal 0. Cool. Another extension, another limit law is this positive integer root law, which is, very similar to the power law, except now we're looking at roots. But again, it's like you can pull that root out and evaluate a simpler limit if you want to. Cool. The limit, all of those y, that y value that you would get out of the limit needs to be non-negative if the root is an even root because you wouldn't want to be taking an even root of a negative number. And so there are exercises in our text that lead you through proving these things if you're interested in proving. Right now, we're just rolling through it and understanding that these things can be added into our toolbox. The rational power law is a combination of the power law and the root law so that, yeah, we can have rational powers and those things can be pulled outside the limit if we want to as well. Okay, so bunch of limit laws. These things work nicely. We can break them apart. That's the big idea for those limit laws. And now we can utilize those to do direct substitution on some things. So if we were given this limit, we've got a rational function there. We know that, rational functions are now continuous on their domain. And we've got some kind of rational power on the outside of the rational function. All of this should work with direct substitution. So it's as simple as just plugging in the x value that we're approaching. We are going to 1. So if I do 5 times 1 plus 3 over 1 squared minus 2 times 1 plus 2 to the 7/3 power, we can just keep evaluating this. We get 8 on top. We get 1 on the bottom that survives to the 7/3 power. And now we get to play with rational exponents a little bit. I think it will be easier for us if we evaluate the denominator first. So if we take the cube root of 8, that would be 2. So this is equivalent to 2 to the 7th power, and then 2 to the 7th power is one more 2 than 64. 128? I think that that is 128 as a final answer. So when we are working with nice functions like this, this is a rational function, we've got a rational power, we can trust that these are continuous on their domain, and instead of having to graph things and look at left-hand limits and right-hand limits, we can just plug the C value in and get an answer for evaluating the limit. Pretty cool. Okay, moving on to algebra tricks. The first algebra trick is factoring. So just to get an example of doing this by hand, feel free to work ahead of me if you want to, if you're confident in your factoring skills. Here again, if we were to plug -3 into the top, we would get 9 minus 9, which goes to 0. And if we plug in -3 in the bottom would go to 0 too. And getting a fraction like 0 over 0 is indeterminate. It doesn't make sense. There will be a different strategy that we learn later on called L'Hopital's rule that will be applicable in this kind of scenario. But for right now, we're going to factor to get rid of this, discontinuity that's in there, or this repeated factor that we don't need. So limit as x goes to -3. We factor the top, it's a difference of squares. X plus 3, x minus 3, no problem. If factoring is rusty for you, I definitely would suggest practicing that some more, so that it doesn't feel rusty and you're ready to go. But yeah, now we have a repeated factor on top and bottom. This x plus 3 can cancel out with that x plus 3, and we would be left with the same thing as 1 over 1. That means that we're looking at the limit as x goes to -3 of x minus 3, and then plugging in -3 gets us to -6 as a result. So we did an algebra trick, then we were able to substitute, all good to go. And again, if you wanted to check that was true, you could totally graph it and look to see that the y value is -6, but you don't have to. we're good to go. Example 6 is another algebra trick where we use what's called the conjugate. So I'll go ahead and write that word, conjugate. But we use this when we see a square root in the top or possibly the bottom that's causing some issue here. So if we were going to 1, we would have the square root of 4 minus 2, which would give us a 0 on top. And on bottom, we'd have 1 minus 1, which would give us a 0 on bottom. So right now, this is not in a form that we can use. But if we multiply this times a special form of 1, we're going to utilize the difference of squares factor pattern so that we change the sign. It used to be a minus sign, but now it's a plus sign. And we don't want to change the value of the limit, so we're going to multiply by this fraction that's just a special form of 1. And what we get to do is simplify this a bit. And after we've simplified this, enough should have canceled so that we could substitute. So if we do the square root of x plus 3 times the square root of x plus 3, we're kind of doing, FOIL now. We're using the distributive property on top. We're going to get x plus 3 as our first factor. Then when we do the outsides, we're going to get plus 2 square root of x plus 3. And then when we do the inside, let's use green. We're going to get minus 2 square root of x plus 3. And that is why we chose this conjugate, so that the middle terms would cancel out and go away. And then the last term would be a plus, oh, no, just kidding, a minus 4. That's good. On the bottom, we would have a bunch of nonsense still. I guess we would want to multiply. We would have x times x plus 3 for our first term. Outside would be 2x. Inside would be minus the square root of x plus 3. And then the last would be minus 2. So that when the dust settles, hopefully some of this will be able to cancel out. On the top, we've got a nice x plus 3 minus 4, because these cancel out with each other. That should give us x minus 1 on top. Combining these two. And then on bottom, it looks like we do have a lot of like terms to collect. All right, we're going to do this in 2 steps so that it's clear. There's the first term. I'm going to bring the third term to the second spot so that we keep the square roots together. I'm going to put this 2x next, and then we'll do the minus 2 over here. All right. So if we try to put in 1 right now, we are going to be thwarted again. And, we would get a 0 on top, and we would get another 0 on bottom. But we can do a little bit more. We can actually do some factoring and do this completely. You won't always have to do this factoring. This one's just extra. So we're going to factor by grouping. These first 2 terms have the square root thing in common. So I can do on the bottom x minus 1 times the square root. That's using the distributive property on the first 2 terms. And then I can use the distributive property on those last 2 terms. And again, I can pull out an x minus 1. and what would be left over is a 2. And so I could do this again. I could pull out a factor of x minus 1 on the bottom out to the front. Yeesh. All right, I'm going to do it real quick because I often get into trouble skipping steps. This already has enough craziness to it. So there's the numerator. I'm using the distributive property to pull out a common factor of x plus 1, or sorry, x minus 1 from both of those terms, so that now we would have the square root of x plus 3. Oh my goodness. Well, that's great. What's the lesson that we learned here? Is that I should have never multiplied these together because multiplying those together led me through this pain and right back to where I started. It was good to multiply the top, however, because we have this x minus 1, tag on it, I'm sorry, um, that we can cross off those common factors, 1, 1, and oh my goodness, limit of x, yeah, as x goes to 1, of 1 over this mess. If you saw this earlier than I did, gold star to you. Thank you for, working ahead and pushing yourself. Um, if you didn't see it earlier than me, can't blame me at all because I didn't see it. Anyways, now we should be able to plug in 1 and be fine. If we plug in 1 in for x, we would have 1 over the square root of 4 plus 2, which is 1 over 4. Blah, blah, blah. Okay, great. Example 6. That was fun. All right, last major method for determining limits in this section will be utilizing the squeeze theorem. For this theorem to be set up, we need functions that behave in this way. F of x is the misbehaving function in the middle. We need to have another function h that is always bigger than our misbehaving function. We need to have a different function g that's always smaller than or equal to our misbehaving function. And the idea is, if we can find a point C as an x value where the limit of h and g are the same, so the top and the bottom end up being the same, it automatically squeezes the function in the middle to have the same exact limit. And so, you know, if we can show that these two limits exist and they both equal the same number, then by the squeeze theorem, we can conclude that the middle misbehaving function also shares that limit. Ooh, and you know, on the street, the squeeze theorem also goes by sandwich theorem or the pinching theorem. Ugh. Um, and yes, there is a proof back in the back of our book. For right now, we're not worried about that. Um, here we go. And I didn't do a great job of erasing this, and that's okay. We can look at this and talk about what we're trying to do. Okay, let's say that we're working with this misbehaving function, x times 1 over sine of x. Let's go ahead and look at this function. Let's get rid of these for now. We're trying to find the limit as x approaches 0. And, zooming in here, it might look like, hey, these, the y values seem to be approaching 0, but maybe from a while back when we looked at zooming in on functions and calculators, maybe we can't be sure that this is actually something valid to do. So we want to be able to show this using the limit stuff that we're learning so far. So this is actually a great opportunity for the squeeze theorem. And actually, this hourglass shape is a great hint as to what functions we might want to use to bound this misbehaving function with on top and bottom. The absolute value of x is going to be a good upper limit, and the opposite of the absolute value of x is going to make a good lower limit. So let's go ahead and zoom all the way back out. This is a little bit easier on the eyes. um, but yeah, this is what the scenario that we're working with. If we go back here, one thing that you might try doing before you realize, oh, hey, I need to use a squeeze theorem, is you might try direct substitution. If you put in 0 in for x, you would get a 0. And then if you put in 0 into this fraction, you would have 1 over 0, which probably looks like something, as x approaches 0, that fraction would get bigger and bigger and bigger and go off to infinity. This part doesn't exist, and this part was 0. Um, this is weird. And it's possible that this overall limit doesn't exist, but it's also possible that this limit does exist. Um, and so what I would consider this to be is just inconclusive. Um, this is like an indeterminate type of scenario. But if we contain this thing, we know that sine of 1 over x is not going to get too crazy. I'm just going to look at that part for now. Sine of 1 over x. Ugh. I mean, it does look crazy at the middle, but when I'm talking about y values, um, the y value of 1 at top is always going to bound this function, and the y value of -1 is always going to, oh, just kidding, y equals -1. That's always going to bound this function at the bottom. Sine's never going to go bigger than 1 or smaller than -1. It's always going to be in the middle, no matter how much crazy that goes in the center. So an idea is that since this is x times the sine, what happens if we replace the sine part with 1 and -1? And the top part could be given by the absolute value of x so that we're always staying positive. Um, if we use just a regular x here, then half of it would be above this function, but half of it would be below. So utilizing the absolute value of x keeps us on top of the misbehaving function, and likewise, the opposite of the absolute value keeps us on the bottom of this. So yeah, recognizing that sine of 1 over x oscillates between 1 and -1 gives us this idea to sandwich this function in between the absolute value and the opposite of the absolute value. Um, and since these three functions have this kind of relationship, the middle one's f, this one's g, and this one's h, um, we can use the squeeze theorem to say, okay, let's take the limit as x goes to 0 of the opposite of the absolute value. Well, that thing's going to go up to a point, and that point is going to stop at 0. The positive version is going to make a V shape down, and it's going to end at the y value of 0. And so the smaller function and the bigger function both share the same limit of 0, and that implies that this misbehaving function also shares that limit of 0. That's the overall thought process behind the squeeze theorem. So really the hard part of this is just finding the top function and the bottom function to sandwich the two between. And oftentimes you're going to be utilizing like 1 and -1 as bounding parts for some trig function like sine or cosine. Okay, so that's good for example 8. We are doing okay for time. Let's get into continuity. L'Hopital's rule is another tool for evaluating limits, but we're going to save that because it involves taking derivatives. All right, so wrapping up this section on limits is talking about the idea of continuity. What we're going to find is the vast majority of the functions that we utilize in calculus are continuous functions. And, we really only want to do calculus on continuous functions if we get stuff, that looks like what we did earlier. Where's the one that had yeah, okay. This is a non-continuous function. And, if we were going to try to find the slope of the function at this point, we would be so out of luck. I guess, here the slope is 0. Over here, the slope is 0. At this point, we're, it's not even continuous. We can't find a slope. Um, so we're going to be looking at continuous functions, ones where we can't pick up our pencil. We've seen this definition of continuity before. What this says is that the limit as x approaches c matches the function value evaluated at c. And you can be left continuous or right continuous, but for the majority of the time, we're just going to be looking at the overall continuity at a specific point c. Um, Here's a throwback to the epsilon delta definition of limit. The main thing that I want to point out is that the only thing that's changed is that this portion used to be L for a general given y value, but now that L is replaced with f of c because we want the function value to equal that specific y value. So, um, yeah, that's really the only thing that's different. The picture that would be going on is the same. The only reason that we don't have a c minus delta over on this side is because they decided to just make the domain of this function start at c. This is a special case of like right-hand continuity without a notion of left-hand continuity. Not a big deal. Okay, so that's there. The only thing that changes is putting in f of c. Continuing on, instead of looking at just continuity at a point c, we can talk about the continuity of an entire function. And we can say that an entire function is continuous on its domain if it's continuous at every point. So there's a little subtlety here that we should talk about. A rational function like 1 over x is continuous on its domain. That was one of the limit law things that we looked at earlier. So this rational function is continuous on its domain, but it's understood that we're leaving 0 out of that domain. The weird thing is if we are asking about, is this function continuous on the closed interval between -3 and 3, this closed interval does include the number 0, and so this function wouldn't be continuous on this interval because it would fail to be continuous at 0. You can see that there's definitely a vertical asymptote there. That is definitely a point of discontinuity. So maybe the first part was more surprising, but we would make the distinction that this is continuous on its domain because for any x values that we are allowed to put in, will still be continuous as we move on. But when we're allowed to put in 0, this function is not defined there, and we would fail this definition of continuity. So it's not continuous on that interval. It would fail at 0. Getting a call. Okay, so I think we're good on this example. Let's keep going, and we'll get some more examples to, flesh things out. I left example 4 already solved so that we could talk about the continuity without having to write a bunch of stuff down. We've got this rational function that we could do a factoring thing if we wanted to find a limit as x approaches 1. But the idea here is that this function should be continuous on its domain because we would implicitly leave one out of the domain. So this one has what's called a removable discontinuity. Um, this is a continuous function on its domain, but if we were to think about the continuity of this function on some interval around 1, then it would fail to be continuous on that interval because we would include the number 1. Um, so yeah, this is a continuous function, but it has a point of discontinuity at c equals 1. Um, yeah, that's what it is. All right. Here are some more properties. These should be reminiscent of limit laws. Here, if we add two continuous functions, the result is another continuous function. Subtraction, constant multiple, product, quotient, provided that this function is not equal to 0 at the point in question. So continuous functions combine together in nice ways to be continuous. All of those follow from the limit laws. Um, Limits pass through a continuous function, meaning that if we're looking at the limit of a composition of functions, here we've got g inside of f, we could pull the function f outside and look at the limit of g, evaluate that, and then plug it into f to get a point here. Now, there are some conditions that we need to meet here. We would need to meet the condition that the limit of g of x as x approaches c matches um, a place where f is continuous in its domain. So it's important that this a matches the a that we put into f. But as long as that condition's satisfied, that things play nicely with the composition, um, the limit can be evaluated in either of these positions, and it works out to be the same. And again, if you wanted to see epsilon delta definitions here, back in Appendix E, there's a cool proof of this theorem. But, not for us. That's okay. Um, Two more quick theorems. A composition of continuous functions is continuous. So if both g and f are continuous everywhere in the domain that you're working with, then you're going to be fine. And um, we would know that a composition of continuous functions is continuous. This is actually a little bit of a more weaker free condition anyways. Um, Also, the inverse of a continuous function is continuous. If you are working with a one-to-one and onto function, then the inverse of that will also be a continuous in the opposite mapping. All right, two more problems, and then we're done. Um, Example 7 has a lot of things that we could look at. The main idea for this is that we're trying to examine these functions and convince ourselves that overall these are continuous or they're not continuous, or we're trying to identify where they're continuous really. Um, so for instance, with part A there, we've got a cube root over a rational function. And, if we split up big F function into a composition of little f and g, uh, where the outside function is the square root or the cube root. So let's make f of x be the cube root of x and g of x be the rational function on the inside, 2x plus 1, x squared plus 5. If we look at this as a composition of functions, we can identify that each one of these is continuous on its own right, and then the composition of continuous functions is continuous. So, um, for, f here, this is continuous, all right? Continuous on its, specifically on its domain. I guess since this is an odd root, then it's going to be continuous everywhere. That one's fine. Um, but we could be utilizing this, the inverse of a continuous function is continuous. We could see that this is continuous because the cube root of x has, an inverse x cubed, and x cubed is a polynomial. It's nice and continuous. So that's one way that we could justify that this is continuous. We could say that this is continuous on its domain because it's a rational function. Um, and then overall, we could say that the composition of continuous functions is continuous. Composition of continuous functions. Okay. So that's, three of those theorems that were listed up here that we utilized. And really, all of these problems are going to have a similar flavor. This one worked out pretty nicely because, the cube root of x is nice. It's continuous everywhere on its domain. If this was an even, root, there might be a little bit more to consider since we'd only want to put in positive values in for that. This rational function is really nice because the denominator here is never going to be 0. We're only going to be adding, non-negative numbers to 5. So this will always be some positive number on the bottom. So there's no asymptotes or anything to this rational function. So this one was particularly nice, but everything here would be of the same flavor. And there might be some more slight considerations, but honestly, it's not too important in the whole scheme of things. Um, we're really just getting practice identifying and kind of breaking these apart and seeing them as compositions of functions. So, for instance, part C, we've got sine as an outside function and this rational function as something on the inside. Here we've got an even root on the outside with a rational function on the inside. Here we've got an arcsine on the outside with a radical function on the inside. And if we tease those apart and considered the continuity of each one of those parts, we could combine them together using these theorems. But honestly, doing one of these together today, I think is fine. I'm not gonna, ask you to do a crazy amount of this kind of stuff. Um, cool. Here's just a reminder that exponential functions are also a class of continuous functions. Um, so that's cool. Example 9 is the last one that I had planned for today, and then stop. This one says, use the above theorems to identify where the following functions are continuous. So again, this one feels a lot like example 7, with just more functions. I think, again, maybe we could just do part A to get a little bit of a flavor for this, but otherwise, we're good. So let's look at part A. Here we've got the natural log of x on the inside of the arctan function, and then we've got a rational portion to this kind of on the outside. So maybe we look at this as a composition of three functions and work our way from the inside out. So I'm just going to write inside towards out this way. So if we look at the natural log of x on the inside, this is continuous on the interval from 0 up to infinity. We're allowed to put, those numbers into a natural log. And we know that it's continuous on that part because it is the inverse of a continuous exponential function. So it's continuous on that domain. Arctan, there. That one's continuous everywhere. The arctan function normally looks like this. And it has yeah, a top and bottom bound at is this pi halves and negative pi halves? It's either that or 1 and negative 1. Either way, it's a nice, well-behaved function that's defined for all numbers that we're putting it in. So, this one's continuous too. We could say that it is the inverse of a nice continuous tangent function, at least on the domain from negative pi halves to pi halves for the tangent function. And then, we've kind of got something over x squared plus 1, and this one would be continuous. Or although, we don't want, that doesn't feel right. Hold on. I guess we're looking at the quotient of two functions. Yeah, so we would say that, these two together would make up the numerator. We could call this w of x or whatever. But then we would have x squared plus 1 on the bottom. It doesn't make sense to write x there. Having a function on top is fine, but it's continuous as a quotient of continuous things. So yeah, I mean, they were working from the inside out. So the caveats on this one would be this thing is continuous, but since we're moving from the inside out, we're only going to be able to put in positive x values into this function. And so we can say that it's positive on its domain, but the domain is just positive x values. A nice thing again about this rational function is that the bottom is never going to be 0. That would be another thing that we would consider. It's something that we would consider on B and C. And, on part B, we wouldn't want x to be the square root of 10, because if we squared the square root of 10, we'd get 10 minus 1, and we'd take the square root of 9 and subtract 3. That would give us a 0 on bottom. We would want to avoid that. Here we could probably factor, and there would be a couple of points that we would need to avoid. That would make the denominator equal 0. But again, I'm not going to crush you guys on this stuff. Really, I want you to just have a flavor that we can break apart more complicated functions and examine the continuity piece by piece. That's the major idea. Next class, next week, we'll start on the intermediate value theorem and we'll look at the limit definition of the derivative. So there's some very exciting stuff coming up ahead. I hope you all have a wonderful weekend. We'll see you on Monday.